Okay, let's start. Good afternoon. So this week we're going to start talking about dimension theory. So we're going to start with what is called topological dimension, more precisely Lebesgue covering dimension. There's a bunch of different topological dimensions also. We're just going to look at one of them, just mention. And then I'd like to talk about box dimension and Hausdorff dimension, to say the least. And then we're going to prove this formula of Hutchinson and Moran that says something about, that relates the similarity dimension of an iterated function system and the dimension of its attractor. But before we get into that, there's some more stuff that I just cannot not mention. I think it's very important, at least for sort of elementary dynamics. Very fundamental ideas. Namely, one of them is perhaps not that fundamental, but still it might be interesting or important to some of you in case you're interested in this idea of the top of a fractal that Professor Barnsley was talking about last week during the talk. So there's this procedure called lifting. That I'd like to discuss a little bit. Then some topological dynamics, some more topological dynamics. So these are certain notions like orbits, pseudo-orbits, and shadowing. This is one part. Pseudo-orbits. And then another part is certain topological properties like topological transitivity, topological mixing, and sensitive dependence on initial conditions, the so-called butterfly effect, but more rigorous. Let me just say SDIC. Sensitive dependence on initial conditions, and then I want to mention this idea of the definition of chaos. So these are what's on the docket for today. So two exercises let's start with. So first of all, here's an exercise. If I have a B-IFS W acting on X with coding map phi sub W, and if the B-IFS is totally disconnected, which means that the images of any two contractions in W are disjoint, in which case we said that this map is a homeomorphism, but it is more, in fact, it's a bi-Hölder homeomorphism. So we had already shown in the Hutchinson coding theorem that this guy is Hölder. So to verify this exercise, you would need to show that the inverse of this function 2 is Hölder. It's a nice exercise. Here's another exercise. This was actually something that I had mentioned at the end of last week, but I want to reiterate because we're going to use this, basically use this idea to handle this lifting procedure. Namely, that we can take a shift space as our ambient metric space, which is it's a compact metric space after all. And I changed notation a little bit. So curly S is going to be my B-IFS acting on Y, S1 to Sn. And what is Si? Well, it takes a point in sequence space, which is just a ticker tape, moves it to the right, right? So take this, move it this way. So now you have an empty spot. And into that empty spot, you put whatever index you had, okay? And so here are things to verify. First of all, this S sub I for any I is a similitude. So for any, or maybe I should write like this, YZ. For any 2 points in sequence space, if I were to look at the distance between the images, it's exactly 1 over theta times this distance. In particular, of course, theta is some number that you fix that is larger than 1, which means that 1 over theta is less than 1, which means that it is a contraction, but it is also a similitude. Right? So in general, a contraction would require this. I'm saying it is stronger, meaning it is this. Furthermore, this B-IFS is totally disconnected, and its unique attractor is the whole space itself. Okay? And upper similarity dimension of this B-IFS is exactly this number. Okay? So you see, somehow, how much a map is contracting depends on the type of metric you're using. And likewise, upper similarity dimension too depends on the metric. That might happen. And in the notes, I have like 5 or 6 different families of metrics next to this d theta metric. I think it would be a good exercise if you're into these kind of things to compute the upper similarity dimension of S relative to these other metrics also. Okay, any questions about these so far? Okay, let's talk about this lifting procedure. The lifting procedure allows you to do the following. You start with any B-IFS whatsoever, and you want to turn it into a B-IFS that has the at least open set property, but in fact, if you can, you want to turn it into a B-IFS that is totally disconnected. And so the lifting procedure allows you to do just that. Okay, so and today I'm just going to give a bunch of constructions or definitions without going too much into details. I'm going to give a bunch of exercises and introduce some sort of possible topics for final projects as well. So lifting. W, B acting on X. B, A, B, I, F, S. So X is complete. W is a finite collection of contractions of X. Okay, so this is the standard object that we were using. What we want is a different B-IFS that I'm going to denote by W hat acting on X hat. So it's acting on a different space. I want this to be totally disconnected. And I want it to be related somehow to the original B-IFS. And related to the original B-IFS, W acting on X. And so the way you do this is this. So you should think of it like this, right? So here you have sort of a B-IFS that is certainly not totally disconnected. Let's say you have this overlapping construction, something like this perhaps. So you want to turn this into a totally disconnected B-IFS, but perhaps on a different space. So what you do is, basically, you take this B-IFS and you couple it with this B-IFS. And somehow that sort of does the job. Okay? So define, so everything I'm going to write here are going to be exercises. Define X hat to be shift space times X. Okay, first let's say that W has n contractions. That's important. This times X. Okay? And I'm going to define lowercase w I hat. It's going to be a function from x hat to itself. So you see I'm trying to define a B-IFS on this new space. Well, I need to feed to x w I hat a pair of a sequence and a point. So omega comma x. What is the image? Well, in the first coordinate, I'm going to use SI. So take the omega, move it to the right, and put I into the empty spot. And in the second entry, I'm going to use the original contraction. Okay. Now, if I were to define w hat as the collection of lowercase wi hats, it turns out that this is a totally disconnected B-IFS. So maybe that's exercise 1. This acting on x hat is a totally disconnected B-IFS. Okay. If it is totally disconnected, well, let's say this first. This is a B-IFS on its own right, I'm saying, which means that it has its own coding map, which is different from the coding map from this guy, of this guy. And that coding map is a homeomorphism. I didn't know if the coding map of the original B-IFS was a homeomorphism, because that's the total disconnectedness property. But since I know, after this exercise, that this new B-IFS is totally disconnected, its coding map has to be a homeomorphism. Which means that there's a shift dynamics on x hat, or rather the attractor of w hat. So let's set up some notation. So attractor of this, let's say it is A sub w. This is this unique compact non-empty subset of x. Coding map of w. Capital Phi sub w, I'm sort of signifying relative to which B-IFS it is a coding map, from the shift space onto the attractor. Now I have the attractor of w hat acting on x hat. Let's call it A sub w hat. It's going to be a compact non-empty subset of not x, but x hat. And then it's going to have a coding map as well. And let's call it phi sub w hat. Again, it's going to go from the same shift space, but this time, instead of this attractor, I need this attractor. Any questions so far? So somehow, the original guy is somewhat pathological. Even though all this machinery works, this is not a homeomorphism. It's only a Hölder, an onto function. Maybe I should write it. So Hölder onto. this guy is Beihilder homeo, invertible. Okay. Now, because this guy is not invertible, I don't have necessarily at this stage an intrinsic dynamical system on the attractor of W, because that I obtained by conjugating the shift on here. Nevertheless, I do have an intrinsic dynamical system there. Okay, so if you want, you can draw this diagram. I'm going to keep writing here. So in the middle, we have the shift. That's sort of our known dynamical system. That's how we're thinking about it. And then we have two attractors, which we think of as unknown things. So this is the original guy. And then I have, let's write it here. These. Okay. Now, there's an intrinsic dynamical system from here to there. You see, because I can say, oh, this F sub W hat is going to be nothing but this inverse sigma this. Okay. Equals, so to go from here to there, I need to go this way, that way. You see, this inverse exists because it's the coding map of the lifted iterated function system. But I cannot do the same thing here because this guy doesn't necessarily have an inverse. Any questions about this so far? Okay. Now, the point here is, though, I want to somehow relate this attractor to this attractor. And so this is the content of the next exercise. And in fact, you can do something more specific. You can relate this coding map to this coding map. The coding map of the lifted iterated function system, in fact, is of the following form. Right? So it has to go from shift space to some set of pairs of, it should be of the form, a sequence, comma, a point in x, because this A sub W hat is a subset of x hat. Which we define to be shift space times x. So it's bivariate, if you want. It turns out that this is equal to omega, comma, phi sub w omega. Okay? That means that because this attractor of the lifted iterated function system is supposed to be the image of the coding map, well, the image of this map is exactly the graph of this function. So that's one exercise. Another exercise is that A sub W hat equals graph of this. Okay? Any questions about any question about this? So this is not the same notion of graph that we were using before in the context of topological Markov shifts. This is sort of like the same sense as you would see in calculus. So you have let's say, a function from x to y, and you can, of course, draw it, right? I mean this function, this subset. Okay, that's a second. And then what I can do is, because x hat is the product of two sets, I have two projections. These are sort of syntactic projections. One of them is, it goes from here to the first coordinate, and the other one is going from here to the second coordinate. Let's call them pi sub 1, pi sub 2. Okay. The image of the attractor under the first projection is everything. The image of the attractor under the second projection is the attractor of the original guy. And this is essentially the reason why Barnsley calls all this stuff the shadow theorem. In a sense, the attractor of the original iterated function system is a shadow of the attractor of the lifted iterated function system. But that is not a very good nomenclature, I think, because there's something called shadowing, which is a technical term, which is something different. And so it's better to not call it shadow theorem, I think. But you can think of it that way, of course. And furthermore, we can complete this graph, this diagram, by saying that if I were to go from here to here using the second projection, based on this, this part of the diagram commutes as well. That is to say, applying the coding map here is the same thing as first applying the coding map of the lifting and then projection. Okay, so these are sort of things for you to verify. Any questions about this? Now, last week on Thursday, during his talk, Professor Barnsley talked about this idea of the top of a fractal. And so let me just point to some references there. He does mention it in the book that we're following as well, but he has another book which is called Superfractals. There, I think the discussion is much more clear. And so if you're interested in looking into these tops and all that stuff, I would suggest you look into that. And ultimately, this notion of the top of a fractal starts with this idea. You first lift, and then somehow you figure out a nice way of choosing, given any point in the attractor, a nice point here. Okay, let me just leave it at that. So, lifting, let's say, evolves into top of a fractal. And for this, see Barnsley's superfractals. Of course, so this is a textbook, so I wouldn't be able to put it under the resources, so you would need to find it yourselves. But I did put some papers of Barnsley that is, I think, related to this idea. So if you're interested in that, you can look into that as well. Any questions about these? Okay, so that's the first item in the docket. Now let's look at orbits, pseudo-orbits, and shadowing. We never defined the notion of an orbit of a dynamical system. So we should probably do it. Okay, here. Some of you have been looking into these notions of orbit and stuff before in weekly reports, but still, I think it's one of the fundamental notions of dynamical systems. So, orbits. Again, you can do this more generally, but let's just look at iterations of a function. So, for x and x, I'm going to denote it like this. Curly O sub x of f is going to be the orbit, and this is nothing but the collection of all iterates of x. So one can write it like this. F to the n of x, where n is a non-negative integer. Okay, that's the orbit. Is the orbit. Of course, if the orbit of a point is finite, that means that that orbit is really like that point is a periodic point, okay, because initially there are infinitely many somehow. But if this thing is counting only finitely many things, at some point you should be repeating things. Okay? But of course, a dynamical system has orbits that are not necessarily periodic also. Okay. So yeah, I guess instead of going this way, let's first define topological transitivity. So you see, for this property, I don't need to assume any sort of structure on X. But for topological transitivity, this next definition I'm going to give, I do need to assume something. You can do this again more generally, but I'm going to leave it to be, I'm going to just take X to be a metric space. And again, I have some function, not necessarily continuous. I'm going to say that f is topologically transitive if there's a point x whose orbit is dense. Topologically transitive. If there's an x in x such that O sub x of f closure is everything. Okay, that means that somehow if this is your ambient space x, there is some point such that if you keep track of where it's going, sort of filling up the whole space. Okay, so you get to approximate any point in x whatsoever arbitrarily closely using points or iterates of x. Any questions about this? Yes.
Wait, so it's basically saying there's like one point where if you start iterating from that point, it would fill up like the entire metric space.
Essentially, yeah.
Okay.
So if you want to be more precise, perhaps let's open this up. You fix this x, that's your nice point. This is what is called the transitive point. That means that for any y in x and for any epsilon positive, there is some n such that the nth iterate of x is in the epsilon ball centered at y. So fn, oh, let's write it like this. D of fnx and y is less than epsilon. For any epsilon, you can do this, which means that if you can do this for epsilon equals 1, so let's say that this is y. So you started here, and then you iterated. Okay, there you go. F to the n of x is here. Okay. But then you can say, oh, what is this? What is this distance? Okay, it's some number that is less than epsilon. Take this distance, divide it by 2. Okay, so that's a new epsilon, which means by topological transitivity, you can keep n go to infinity, and then you know that it's again going to return, and so on and so on. Okay, does this sort of make sense? It seems like a bizarre property, but most dynamical systems that we can say something about has this property. For instance, the shift dynamical system does have this. Exercise, shift is topologically transitive. We had discussed this exercise with one of your colleagues, but this is a nice exercise to think about how to handle. Because ultimately, this is sort of like some notion of recurrence. Like things have to keep returning to themselves in a sense. Like you can think of it like this. Say your dynamical system is not topologically transitive, which means that there is some point that no orbit can approximate arbitrarily well. That's sort of like an isolated point. That's almost like a different or separate dynamical system. You might as well do this, right? Like you can say, oh, there's this part where things are transitive and there's this other part. And indeed, there are theorems like spectral theorem and stuff. This is a nonlinear spectral theorem that essentially does this. Even if your dynamical system is not topologically transitive, that's not exactly the statement, but that's sort of like the main idea. You can split it into basically, a bunch of building blocks, each of which is topologically transitive, and so on. And then what you can do is you can understand each of those pieces and then put them back together, and so on. But this, the shift, is topologically transitive. Maybe I should say something. So for instance, if the shift space has n symbols, I need to find one point whose orbit on the shift approximates any other point arbitrarily well. Let me just leave it to you to verify that indeed, if I were to take omega, let's just say n equals 2 actually, easier. I'm just going to take the block codes that determine the periodic points, and I'm going to put them side by side. Okay. So I need my ticker tape here. Because in shift space, approximating some other point using some sequence is saying, oh, I need to take the first k, let's say, entries equal. Okay? So what you can do is you can just list any first k entries. So this would start like this. So blocks of size 1, I have 2 of them, 1 and 2. And then blocks of size 2, 1, 1, 1, 2, 2, 1, 2, 2. Now I need to put all of them, basically. 1, 1, 1, 2, 2, 1, 2, 2. And it looks like perhaps this is like cheating, but this is the sort of power of the shift spaces. It's like basically like a computer. You can sort of like describe what it's supposed to do in terms of itself and so on. Okay. So 1, 1, 1, 2, 2, 1, 2, 2, and then I need to have blocks of size 3. So I have 8 of them, I think. Yeah. So 1, 1, 1, 1, 1, 2, 1, 2, 1, 2, 1, 1. And then I need to keep going. And you list all of them like this. And then now it's your job to verify that if I were to keep iterating this under shift, which means that I'm just like moving this way, this approximates any sequence whatsoever arbitrarily closely. Any questions about this? Okay. Okay. Here's another exercise. If F is topologically transitive, there's a different way of stating this topological transitivity in terms of hitting times is what they're called. Is topologically transitive if for any non-empty open subsets U and V in X, there is an N such that the nth iterate of U under F hits V. So what you should imagine here is that here's your ambient space, here's your U. It's one part of the ambient space, and here's some other part. Now you keep iterating. You keep this piece static, and you let your dynamics move and like transform this part, this little piece. And what happens is something like this. Of course, it starts bending and so on. So let's say that this is f of u, and then maybe it's like this. This is f squared of u. And then you wait long enough, there's at least one point that hits this, that is in the intersection. Yes?
So like, it makes sense like in the case of like subsets, but can this work for discrete points too? Say you're in like a continuous metric space, but then you just have like two discrete points.
Well, I mean, that depends on whether or not those points are isolated, because I'm saying open subsets.
Okay.
So they have to have some thickness. Okay? So open subset, remember, has, so given any point in the open subset, there's an open ball that is completely inside the open subset. So you can sort of like wiggle the point around without leaving the subset. Sorry, if f is this, then this. And it turns out that in most situations, this is also, this works backwards as well, but you need to have some conditions. One of them I'm not even going to define. If x is complete and this is the term that I'm not going to define. Second countable. It's a certain topological property that says you have basically, I'm not going to say it because it's going to get complicated. If you have these two properties, then the converse is true also. Let me just say, though, that any compact metric space is, of course, countable, of course, complete and also second countable. So for most application purposes, your ambient space X is compact, which means that you can sort of take this as the definition for topological transitivity also. Okay, maybe I should write that. Compact metric, complete, second countable. You don't even need completeness, actually. You need something called bare property, which we haven't discussed, and I'm not going to discuss. Also, I think I wrote some stuff in the notes if you're interested, but these are certain properties that you learn in topology classes and so on. Any questions? Yes?
You cannot answer this if you don't want to, but can you give me an example of a non-second countable metric space?
Probably some function space.
Okay, yeah.
Because for metric spaces, second countable is equivalent to separability, which means that you have a countable dense subset. And probably the easiest way to break it is to use a function space or an infinite dimensional space. Yeah. Yeah. Probably there are better examples, but honestly, I don't think about these kind of things. So okay. I mean, we can discuss it later if you want. I know you like separation axioms, so. Okay. Any other questions? Okay, so the reason why I introduced this is this. So you see, the orbit of a point under a dynamical system is a certain subset of X. And we're thinking of X as the space. And when I'm writing it like this really is the monoid of non-negative integers acting on X. And we said that that monoid was the time. And in fact, what you can do here then is that you can take this property and turn it into a subset of the time space. Okay, so that's the space of, that's a set of hitting times. Okay. So for any subsets A and B, I'm going to define this. So I'm going to write it like this. Hit to the power F, so the hitting set relative to the dynamical system. F from, let's say, B to A is going to be the set of all those times such that this occurs. N such that Fn, f to the n of B inter A is non-empty. So you're supposed to think of it like this. This is a bunch of time points. And you have two subsets, and you're trying to go from B to A using iterates of F. And you're just looking at the times that actually makes this happen. And so this property says that topological transitivity is basically equivalent to saying that for any pair of non-empty open subsets, the hitting times set is non-empty. Now you can ask for more. Okay, let's write it like this. Exercise. In fact, if you have topological transitivity, not only you have that the hitting times is non-empty, but in fact it is infinite. That's first. Then for any UV non-empty open, the number of hitting times from U to V, or from V to U, doesn't matter of course, is infinite. Then you ask, what type of infinite? Because you can have sort of, you can have a subset that goes to infinity whose complement is also infinite, or you can have a subset that is infinite whose complement is finite. That property is of course stronger, and that is what is called topological strong mixing. Is topologically strong mixing if for any non-empty open subsets U and V in X, if I were to look at the hitting times, it's in fact containing every single n after some capital N. There is an n such that the set of hitting times from V to U is all times except the first n. So this is something stronger than topological transitivity. And the picture you should have is this. And this is my X, here's my U, and here's my V. I guess this time I'm fixing U and I'm letting F move F, and F move V. And so if I keep applying F to V, this guy keeps sort of like distorting. This is F of V, and then somewhere here is F squared and so on. For topological transitivity, all we required was that at some point you had this non-empty intersection. But now I want something stronger for topological strong mixing, which is that once I hit once, there is somehow that after that time, there is no way these two sets are going to be separated. So if you keep iterating, there is always some intersection. Okay, that's stronger. Now there's also weak mixing. I'll leave that to you to find. So we find topological weak mixing okay. Once you define this, show that topological strong mixing implies topological weak mixing, which in turn implies topological transitivity. Next, verify that the shift dynamics, in fact, has topological strong mixing property. Okay. Here is topological strong mixing. What else? Okay, so this is a nice exercise. Find counterexamples. There are examples of dynamical systems that are topologically transitive but not weak mixing, and weak mixing but not strong mixing, and so on. Let me just write this over there too. For converses. A good avenue to come up with examples are, of course, subshifts or subshifts of finite type. Now this, so let me mention this. So these type of properties, these are what one might call topological ergodic properties. There are a sort of true ergodic properties or statistical properties that you can associate to, that you can give to dynamical systems, but that requires a lot of, well, some amount of measure theory that we're going to discuss a little bit, but this is sort of like a light version of this business. There's this Bernoulli property, K property, bunch of different mixing properties with certain rates, ergodicity, and so on. But this is sort of a good introduction. And one of the things that people do is you have a bunch of properties and they're trying to come up with examples of dynamical systems that satisfy, let's say, the 1, 2, and first, second, and third properties, but not the remainder. So this is sort of about understanding the flexibility of these type of properties. In this case, one implies the other one, so it's clear which one is stronger than the other one, but there are, when it comes to sort of like more hardcore ergodic theory, there are more complicated properties like central limit theorems and so on. Some of you have been sort of encountering in your reports ideas that are related to these things, but still, these are all like active research topics. Okay? Question, yes?
For topologically strong mixing, like, if I were to, so we have contraction mappings, can I think of that like an expansion mapping, like a mapping that takes up the whole space eventually?
Yeah.
Like a subcategory or something?
Yeah, you can think of it like that. Of course, in dynamics, we have 5 different senses of expansion as well. There's expansivity and so on. That's its own thing, but yeah.
Was it kind of like related to like basin of attraction where like, you know, you get like pulled into some subset and it might leave, but it'll always like return to that subset?
Yes, but you want things to grow ultimately. You don't want things to shrink, like your colleague was mentioning. So in the context of just an attractor, so attractor in the sense that we're using, that's not quite exactly what we want. But maybe if you have something like a strange attractor, where somehow you have attraction, but somehow along certain directions you have repulsion as well, which is why they're called strange attractors. Hard to understand perhaps a little bit. I mean, nowadays people use different gadgets to make this idea more formal, of course. There are these things called Lyapunov exponents that we sort of mentioned last week a little bit, but this is just the starting point. Okay, so when it comes to subshifts or topological Markov shifts and so Markov chains, these properties are rather straightforward to handle. But when it comes to more general abstract dynamical systems, or dynamical systems that you encounter in the nature, let's say you have a dynamical system given to you by an applied mathematician because they think that it models something. Okay, so does this have this property and so on? It becomes hard to analyze those type of things. Any other questions about this? Okay, let's take a 5-minute break. Let me get back. Another barrage of definitions and exercises. I go back. Okay, welcome back. So, sensitive dependence on initial conditions. We're slowly getting closer to this notion of chaos, or at least one definition of it. So this is basically, in the sense of Jeff Goldblum in Jurassic Park, where he's talking about butterfly effect and so on. This is the formal version. You say that a dynamical system, again, I'm just looking at iterations, has sensitive dependence on initial conditions if, well, the basic idea is this. You start at one initial condition, that's your x, and then you keep iterating it, and you go somewhere. And you call the dynamical system, you say that it has sensitive dependence on initial conditions if just a little bit of a change of the initial condition make the trajectories diverge. Ultimately, that's the idea. So formally, if there's an epsilon star such that for any x in x, so that's your initial condition, and for any epsilon, that's your error, there is some other initial condition that epsilon approximates the original initial condition, but nevertheless, ultimately, at some time n, they are separated. So maybe I should draw a picture here. So you should think of it like this. Let's draw it like this. Of course, this is like a caricature. The trajectory of x doesn't need to be sort of like a horizontal line. That doesn't even need to make sense, but let's say that this is going like this, okay? So this is your epsilon ball. For no matter how small the epsilon is, there is some y, epsilon close to x, somewhere here, such that when you start iterating your dynamics with base point, with initial condition y, and so let's maybe be more specific actually. So that's x, and then f of x, and somewhere here is f squared of x, and then f cubed of x, and so on. And then you're trying to, you're sort of looking at the epsilon star balls centered at these points in the orbit. These are all epsilon star balls. Sensitive dependence on initial conditions require this, that there is a y, epsilon close, such that when you keep iterating this, eventually, maybe initially it's going to stay near f. Maybe this is f of y, then this is f squared of y, this is f cubed of y, and so on. But if you wait long enough, now the trajectories are separated by this epsilon star. That's the notion of sensitive dependence on initial conditions. Now, nowadays people look at more sort of quantitative versions of this as well, but this is sort of like a good starting point. One exercise, of course, is that the shift dynamics has sensitive dependence on initial conditions. Another exercise, we didn't discuss this dynamical system that much, but this is also one of the natural examples. This is not in the context of this stretch and fold dynamics, but still it's very important. This is what is called the rotation. So you have the circle, and you take any initial condition, and you add some predetermined number alpha to it, and then you need to take the mod 1 so that you can keep iterating. So you sort of like start with at a point, and then you rotate it by alpha, or 2 pi alpha, depending on how you're thinking about it. In any event, that doesn't have sensitive dependence on initial conditions. So somehow this sensitive dependence on initial conditions is part of this stretch and fold dynamics, or hyperbolic paradigm. this rotation dynamics is a different paradigm. It's what is called elliptic paradigm. So the methods for that is very different from the things that we were discussing in this class. Another exercise, this is in case you know linear algebra. If I have a linear transformation on Rd and no eigenvalue of it has modulus equal to 1, so maybe it's less than 1 or greater than 1, then it has that dynamical system, iterations of the matrix has sensitive dependence on initial conditions. Okay, questions?
So
yes.
Is the reason like epsilon star and epsilon different, so you can say like they get arbitrarily far apart from each other?
I mean, so this epsilon star is, in a sense, sort of a number that is associated to the dynamical system itself. But then this epsilon tells you how much you can approximate. Like you could, if there's an epsilon star like this, you could choose like epsilon star divided by 2 as well. But this is sort of like some gap that this SDIC property guarantees you're going to have if you wait long enough. This is sort of also related to this other property called expansivity, but I don't want to get that much into that as well. Yeah.
Like how do you choose like how large or small your epsilon ball would be? Because like theoretically, like say you're using like a Lorentz system, couldn't you pick like a ball of like some radius?
Well, that's the point. In order for SDIC, no matter how small you choose it, you should be able to find a nearby point that diverges. I mean, admittedly, this is not a very, perhaps, computational statement. But I bet there's more sort of quantitative versions of this that you might find more useful. Yeah. Yeah, let's talk about this later. That's an interesting question, actually. Yeah. Any other questions? Okay, so now that we have all this, I can define this notion of chaos. And I wanted to prove something about this notion of chaos, but because we're running short on time, I'm just going to leave it as sort of like a fact, but it might be a very nice final project, ideas related to these things. So, definition. And this is the definition that Barnsley gives as well, but let's say this. I have F acting on X. I'm going to need X to be a metric space at the very least. Metric space. F is said to be chaotic in the sense of Devaney. Devaney was, or I think still is, sort of one of those mathematicians who wrote sort of one of the introductory books on dynamical systems back in the 80s, I think. And there he was using this definition. And so it became sort of popular. People looked into it and so on. F is called chaotic in the sense of Devaney. If you have the following three properties. First, that F is topologically transitive. Second, that the periodic points of f, which is a subset of x, is dense. That is to say, you can approximate any point in x whatsoever by some periodic point of f. And third, f has the sensitive dependence on initial conditions. Exercise. Shift is chaotic. And at this point, you should also compare this statement. So for instance, this statement here to one of the items in the Hutchinson coding theorem, where we had something like, oh, the attractor is a closure of the union of all fixed points of all contractions in the monoid generated by the iterated function system. That's sort of like modeled after this property, actually. So, how is this related to, or how can you turn this into a final project? We can do this. In fact, let me just write it here. This was something that was discovered after Barnsley's book was published. Some people realized that, in fact, the third property is implied by the first two. Banks et al. Banks all. And also, there's another paper by Glasner and Weiss. Showed that 1 plus 2 implies 3. So really, this saying for the definition of chaoticity, that f has sensitive dependence on initial conditions, it's a redundant statement. So ideas around this, you can sort of, I think it would be nice to package into a final project. And further references are, of course, Sternberg's notes and Milner's notes. Okay. So this Glasner and Weiss paper is somewhat more upscale compared to this, but depending on your time and stuff like that, that might be sort of like something that that interests you. The argument is not that complicated. I was planning to do it, but it's just going to take some time, and I don't want to sort of introduce more proofs because we're going to switch over to a different topic. Okay. Good. And there are a bunch of other definitions of chaoticity. I think nowadays, so this is, back in the, a popularity of this, chaos theory, butterfly effect, and so on, as exemplified by Jurassic Park. This is like the Jurassic Park, in a sense, is the end of this era where people were very interested in chaos theory and, attractors and fractals and so on. And so now mathematicians, or other people too, have digested all these ideas, and they're not that interesting anymore, perhaps. And people are not that interested in defining what chaos means nowadays, as far as I know. They just take something. They say, for instance, the optimal exponent is positive, and that's like a very specific thing, and they go with that. It's a lot more complicated, of course, than these kind of things. But anyway, so back in the day, people were interested in, at least, pure mathematicians, let's say, were interested in definitions of, what it means for a dynamical system to be chaotic, or, what is an attractor, and so on. But nowadays, these are just like some buzzwords from the 80s. So all of these papers, so these two papers and these notes are also under the resources. So if you're interested, you can have a look and see. Okay, any questions? Okay, so you have 2 minutes. Okay, I might continue talking about this on Thursday a little bit because I wanted to mention this pseudo-orbit business and the shadowing property. So you see, in a sense, somehow I said, the shift dynamics is the best type of dynamical systems, but it seems in a sense it's the worst. Like chaotic seems like it's something that we would have trouble understanding, but the modern perspective of dynamical systems is sort of the other way around. The more chaotic it is, somehow it turns out that unstable systems are stable in their instability. So you get to use them somehow. So something like this rotation is, it doesn't have this chaotic property, but that makes it harder to understand in a sense. It becomes very specific somehow, the numbers that you're using and so on. Okay, so here's the idea of the pseudo-orbit. So we defined the notion of an orbit. A pseudo-orbit is going to be, instead of giving the formal definition, I'm going to give you the picture for now. So here's the orbit. We have x, and then somewhere here is f of x, and then somewhere here is f squared of x, and then here f cubed of x, and so on. Now a pseudo-orbit is sort of like a more computational version of this. You say, if I'm trying to use a computer to model this, I will never be able to sort of iterate whatever initial condition I have, which is going to be a number, with exact precision. Maybe there's some truncation. So instead of applying f squared, instead of applying f to f, so this is f, this is f. Instead of applying f to f of x, maybe I'm going to truncate it. Imagine sort of like a floating point arithmetic. And instead of applying f to this point, I'm going to apply it to this point. So it's going to go somewhere else. And then I'm going to truncate it again and apply f to that approximation. So really, instead of looking at iterates of one point, I should really think of having some error at each step. So maybe those errors are going to sort of like add up, and ultimately this, whatever I'm iterating, is going to go to some place. That's the notion of a pseudo-orbit. Shadowing property tells you that even though that might be true, that you have sort of like these errors that you introduce at each step, somehow we can manage it. Okay? Let me just leave it at that. On Thursday, we're going to discuss this more specifically. Thank you. Okay, hello, good afternoon. So today, I'd like to finish discussing the pseudo-orbit business and shadowing, and then we're going to start talking about dimension theory, but not this dimension theory from a more analytical point of view, but rather I'd like to start with this topological notion of dimension, or one of them, which is this Lebesgue covering dimension. Before that, I should mention that some of you started submitting your topic, your choices for the topic for the final report. Try to be as specific as possible. Like instead of saying, I want to study this idea or this paper or whatever, you want to have sort of like a thesis. And if you're writing sort of like a humanities paper, your thesis is that you argue this is the case. Whatever blah, blah, blah should be a human right. Right? That's your thesis. And there should be something like that in your topic as well. So obviously in math, you don't have sort of these opinionated things, but it's a theorem or it's a problem. You can pose a problem. I don't know the answer to this question. I want to try to answer this question, which is like a math. So you want to formulate it in such a way that it is mathematically answerable. Right? Like not all questions are like that. Yeah, being as specific as possible would be the best. And instead of sort of expanding, or instead of sort of, you know, describing a bunch of different things at the surface level, I would suggest that you pick one topic and try to understand it and try to sort of describe it in as much detail as possible. That's better, I think. Any questions?
So like, could we say pick a particular theorem from a paper?
Yes.
And then be
Yes.
towards it?
Yes. Yes.
Okay.
So the one thing that I was curious when I was like starting this and specifically looking at that like digits problem, for example, is even with the whole bunch of other papers, should I include those on my references even though I haven't read them yet? Or,
Yeah.
okay.
Yeah. Potentially, it's like you may sort of like have a look at this and that paper, and even if, I mean, I'm not expecting you to have read the papers so far, but at the very least, you should have an inkling. Like a lot of the things that I'm discussing, you should think of it like this, right? So, so one example of what I'm, I guess, asking for is something like this tentative schedule on the syllabus. Like many of the theorems that I wrote, or many of the ideas, I had some idea when I was preparing this syllabus, but as we're getting closer and closer to actually discussing that theorem or that definition and stuff, I sort of like understand it better. So you see, I had some idea as to what the plan is, and I'm trying to sort of follow these topics or theorems, whatever, as closely as possible. So that's one example that you can keep in mind. Another example is that, you know, a couple of times during lectures I've given previews of things that we're going to do. Like even in week 1, I think I mentioned this Hausdorff measure, or, you know, whatever. I didn't go too much into detail, but I said, you know, something like this should be true. And then I gave the preview for the Moran-Hutchinson dimension formula, for instance. Right? So I gave parts of it. I didn't define the Hausdorff dimension and stuff like that, but I said once we define it, it's going to make sense. But at least so far, you know, there's this other thing that we can compute, and this formula gives inequality between these expressions, whatever this other expression is. So you should think of it like that. Another thing, of course, is that like you should be aware of the prerequisites of whatever topic that you're going to study, because, you know, X topic could be, you know, familiar to you, but so for instance, one of your colleagues is interested in Brownian motion, which is a, you know, very good topic, but in the report you should try to ultimately make the report as self-contained as possible. Okay, so that means that you're going to have to do some exposition as well. Okay. Any questions about these? I mean, which is good, you know, because ultimately I'm asking you to do something in 5 to 10 pages or maybe more, depending on what you're trying to do. But at the very least, you should have the definitions and so on. Okay. Pseudo-orbits. Here's the formal definition. Let X be a metric space, and I have a function f from X to itself, so it's a dynamical system. I'm not assuming that f is continuous at this stage, and I don't need to assume it. This is the definition that I'm going to give for shadowing doesn't require it, but often when you want shadowing, your dynamical system is continuous, of course. I fix a delta, that's going to be my error margin, and a sequence of points. Okay, so X bullet. I'm going to call X bullet a delta-pseudo-orbit for f if the following happens. Okay, so let's look at this expression here. Here I have sort of this marked point at time n given by this alleged pseudo-orbit. And somewhere here, let's draw it like this, is the next marked point. So what I'm going to do is I'm going to apply f once to this guy, and I'm hoping that when I apply f to this particular point in my sequence, it's going to land somewhere near the next point in the sequence. So let's say lands here. So this is my delta error, okay? And I want this error to be bounded. So that's why I'm taking the supremum over all n. So I'm looking at the distance between f of x0 and x1, and then distance between f of x1 and x2, and so on. And you can also think of it like this too. This is sort of like a more abstract way of thinking about this, and I'm going to say a couple more words about this in a second as well. But this is sort of like a conjugacy relationship, okay? So here, up top, we have the non-negative integers and this successor dynamics coming from the piano axioms, right? So this is just a dynamical system that takes whatever number and adds 1 to it, which is this very straightforward dynamical system. This x bullet is really, I'm thinking of it as something like a conjugacy. Of course, it's not going to be a bijection necessarily, but at the very least, it should be sort of a semi-conjugacy. And so I'm saying that this, so if I were to start with n here, goes to n plus 1, and then if I apply this guy, I get the n plus first term. But instead, if I were to go this way first, I have x sub n, and of course, if I were to apply f to it, I would get f of xn. And I'm saying that basically these two things should be the same. So that's why I wrote here, up to a delta error. Okay? So it's not really a conjugacy, but it's a conjugacy up to a delta error, up to a uniform delta error. If I have another sequence, y bullet, and some other number epsilon, I'm going to say that y bullet epsilon shadows x bullet if the corresponding terms of the two sequences are never more than epsilon away from each other, which is sort of like this idea. Here I'm not using f, but still. So I want yn to be here, maybe yn plus 1 to be here, and this is epsilon. And again, I want this error to be bounded. Any questions about these definitions so far? So I'm going to say that f has the shadowing property if the following is true. So if for any epsilon there's a delta such that any delta pseudo-orbit for f is epsilon shadowed by a true orbit. So before writing that down, perhaps I should say, what is a zero pseudo-orbit? Well, that's just an orbit, of course. For any epsilon, there's a delta. For any delta pseudo-orbit, x bullet of f, one can write it like this. There is some x in x such that y bullet defined by the iterates epsilon shadows x bullet. Okay. So this is really saying or in other words, another name for the shadowing property is the pseudo-orbit tracing property. And people also say that Y bullet traces X bullet. So the picture is this. So you first fix your epsilon, and you want this delta, you want to be able to find a delta such that the following happens. Let's draw it like this. So this is, let's say, x0, and then x1, and then x2. This is my epsilon. I want a delta that's going to be probably much smaller than epsilon, but not necessarily. Such that if it happens that f takes x0 to some point inside the delta ball centered at x1, and likewise f takes x1 to some point inside the delta ball centered at x2, maybe it's here, and so on for all n, then somewhere here is an x such that if I were to apply f to x, it's going to land into the epsilon ball, and then its further iterate is going to land into this, and so on. Does this make sense? Yeah.
Is it like, it has the shadowing property if any like delta-pseudo-orbit like approximates the true orbit? Is that kind of like the idea?
It's the other way around, actually. You can think of it like that as well. But so the pseudo-orbit you want to think of as something that is given to you by a computer. Let's say that at each step you're truncating, so you're sort of like leaking some information. And you want to say, okay, the trajectory that the computer draws, does that have anything to do with the actual dynamical system that I'm trying to model? And this is saying that even though maybe it is not exactly that, up to some error that is arbitrarily small, there is a true trajectory that is being represented. Yeah. So this is sort of kind of paradoxical because so last time we talked about the sensitive dependence on initial conditions, which says that the system is sort of nearby orbits diverge, but at the same time, it often happens to be the case that sensitive dependence and shadowing property go hand in hand. And indeed, the shift dynamics does have this property. And of course, that's going to be an exercise. has the shadowing property. And rotation on the circle doesn't. So f of x equals x plus alpha for some fixed alpha mod 1. Recall that this shift dynamics, or doubling and all that stuff, these were in the context of this hyperbolic paradigm in a stretch and fold paradigm. And then I said that this second type of example, rotation, it's a different paradigm, this elliptic paradigm. So the methods really are different and mostly different, let's say, in this context. Okay, and in this class, we've been mostly focusing on this hyperbolic paradigm because that's sort of like the paradigm where we sort of see iterated function systems, or at least the types of iterated function systems we were looking into. Okay, yes?
What's the strength of the shadowing property being this instead of just making a claim of like there's a delta-pseudo-orbit for every delta greater than 0? Like, it seems like we're doing a bunch of things, and I'm wondering what the difference between those two definitions. Like, what am I missing with that definition?
Can you repeat the question?
Yeah. So if I had a different statement that was for all deltas greater than 0, there is a delta pseudo-orbit. Why is that property weaker than the property that we have for the shadowing property?
Oh, because you can always, most often, you can generate delta pseudo-orbits. That's not a major problem. So the problem, what you really want is that near the delta pseudo-orbit, you want an actual orbit.
If we know that we can take the error to 0, if we can say for all delta greater than 0, I guess how do those differ?
I see. I mean, in one version of shadowing, you do want something like that ultimately. Not only you want this, but that you want delta to be a function of epsilon that decays to 0 as epsilon goes to 0. So that's a slightly more sort of, there are like more quantitative versions of this. So there's something also called specification. I put some papers under the resources about this. So not only do you want this, but in fact, you want sort of like more complicated markers. And you want to do something like this, in fact. So this is specification. And at this point, no matter what I write, you should expect that shift dynamics has this property, okay? So you want to have something like this. You want to have sort of, instead of sort of infinite segments of pseudo-orbits, you want to have finite pseudo-orbits, but you want a bunch of them. Let's say that you have here one pseudo-orbit here, and then somewhere else you have here another pseudo-orbit, and then maybe you have another one over here. Specification really says the following. If you have a bunch of these pseudo-orbits that are not really related to each other, you can in fact find one orbit that stitches all of them together. So you can sort of like turn them into a combo. Second.
Another true or a pseudo?
True. Actual.
I just might have missed missed this, but how is like that sequence of points, like the x0, x1, how is that defined in the first place?
You just take it.
Okay.
I mean, how do you take a sequence of points in a set in a metric space? You just, sample it.
Yeah.
So you take one point, you look at its image. Okay, so you take x0, take a random point. Look at f of x0. x1, you have to take it in a delta neighborhood. You fix the delta as well. That's one way. Another way, which is sort of like also useful, we also didn't discuss this too much, but there's this whole idea of perturbations. So you can look at, instead of one dynamical system, you want to look at the space of dynamical systems. Because you see, this is really about managing the errors that you introduce when you're observing something. Now, it could be that error could come from two different situations. One of them could be because of the initial condition. Maybe you're not able to see the initial condition properly. That's the first one. But the second condition is that maybe you can't see the dynamics properly. Okay? So how do you sort of formalize that idea? Well, you look at the space of all dynamical systems, you think of it as a metric space, and then you sort of like perturb your dynamical system a little bit. So for instance, this is, let's say, the space of all continuous functions from x to itself. This is a metric space. And if x is complete, this is also complete by the supremum norm or supremum metric. We sort of discussed one version of this in week 1, but I didn't spend too much time on this because this is sort of like an infinite dimensional space if you want. And it's a function space, and it's slightly more sophisticated, or it's more complicated, let's say. So how do you define the distance between two functions, two dynamical systems? Well, you take the distance between f of x and g of x, and then you take the sup over x's. Okay? So let's say that this is your dynamical system. But maybe you can't really see this. Maybe you see a perturbation of it in the space of dynamical systems. Let's say it's a delta perturbation. And really, instead of being able to iterate f, you can iterate only g. So you can think of it as, that perturbation is the truncation you're doing at each step. Right? So because if you have sort of like a function on the interval or something, and if you're sort of truncating after each step, that's sort of like a different dynamical system, actually. You're iterating not f itself, but f composed with truncation. Okay? So this is a dynamical system in and of itself. So it has orbits. But any orbit of g is going to be a pseudo-orbit for f.
Okay. Makes sense.
So any true orbit of the delta perturbation of f is a delta pseudo-orbit. Of f. And then you want to say something like, even if I couldn't see the dynamical system properly, could I say something about it? Okay, so you see, this is sort of like a different perspective from sort of like a more algebraic perspective, if you want. So if you had sort of like the doubling map or something like that, you're drawing it like this. It's a beautiful thing, but it's straight lines. But you want to say something like this instead. Oh, maybe I have sort of like a kink over here. Now what happens? Or you want to say things that is independent of the algebra that is available in the linear setting. Okay, so we're not doing algebra; we're doing dynamics. Okay, so I mean, the algebraic examples are still very useful, of course, but ultimately, whenever you have something nice, algebraic, you should be aware that there's a bunch of like extra structure that you're using that you won't have available in general. Yeah. And then there's a bunch of different ideas like structural stability and stuff like that that allow you to sort of say, oh, if I were to perturb this a little bit, they're actually topologically conjugate and blah, blah, blah. There's a lot of theory about this. Yeah. Any other questions?
Do we need sensitive or non-sensitive dependence on initial conditions for that statement? Any true orbit of the delta-perturbation of F is a delta-pseudo-orbit of F?
No, it's a general statement.
I guess, well, so then it seems like if I plugged in a point to G instead of F, it could take me a little bit farther out, and then after like the 12th iteration, it's outside the delta ball.
Well, I understand, but I see.
So does that mean like the system can't be chaotic?
No, that is not true. That is not true. Because of this. I want F and G to be close like this. Okay, that's an exercise. It's a good exercise, actually. This is a very strong condition, really. You were saying?
Oh, I was just gonna build on that. Like,
Oh,
I think
okay.
that means like the system can't be chaotic.
No, it is chaotic. That's the thing.
Okay, yeah.
Yeah.
I see now.
That's the paradoxical thing. Instability is a stable thing somehow. Okay? Yeah. I mean, think of it like this, right? So the behavior of this rotation dynamics is highly dependent on this number. Right? If you were to try to sort of model this, let's say that alpha here is 1 over pi. So it's an irrational number. Okay, you're going to truncate it in a computer. And you're going to see that all orbits is going to be periodic. Because it's a rational rotation is what it's called. But actually, alpha is not rational, and no orbit is periodic. And in fact, all orbits are dense. Okay, so you see this is very specific. The behavior of this guy is very specific to this particular number. So in elliptic paradigm, perturbations are a lot harder. People still do it, of course, but techniques are different. Okay. And then one of the things you can do is you can sort of mix and match a little bit. You can say, oh, you know, I have not completely hyperbolic or not completely elliptic, but some hyperbolic and some elliptic. And that is called the partial hyperbolic paradigm, which is sort of like a big area nowadays. And there's also this other paradigm, which is this parabolic situation. And let me not get into that. It's sort of like in between these two. Okay. Any other questions? Good. So let's just connect this back to iterated function systems. Oh, I should mention, or maybe it's an exercise now, that shadowing property is invariant under topological conjugacy, which means that if I have two metric spaces, two dynamical systems on each of them, and there's a topological conjugacy, then one has shadowing it if and only if the other one does. So maybe I should write that there. If is a topological. So it's a homeomorphism that conjugates the actions. Topological conjugacy from F to G. Then F has shadowing if and only if G has. And likewise, F is topologically transitive if and only if G is, F is topologically mixing, and so on. All of these properties really are invariant under topological conjugacy. Maybe I should add those as well.
Can I just verify that topological conjugacy, is that like dynamics preserving mapping? Or what?
Yeah, you can think of it like that. Yeah. Similarly, for topological transitivity, topological weak mixing, topological strong mixing. So for instance, if you believe this, you cannot conjugate shift to the rotational dynamics, for instance, because one has shadowing, the other one doesn't. Okay, so I wanted to say something about this, but I'll say something about it in a second. So let's connect this to the iterated function system theory. Let's look at a totally disconnected one. Right? If the original iterated function system is not totally disconnected, of course you can do this lifting procedure to get the totally disconnected iterated function system and apply whatever I'm going to say to that. So say I have a B-IFS that is totally disconnected. I have a conjugacy map, or a coding map, from shift space to the attractor. That is a homeomorphism. And since on the shift space I have the shift dynamics, I have the intrinsic dynamical system associated to the iterated function system acting on the attractor. So we define this as phi composed with sigma composed with phi W inverse. Now this is the dynamical system acting on A sub W. And by construction, you see this dynamical system is topologically conjugate to the shift dynamical system, which means that this too has the shadowing property. Which means that if you're trying to understand this intrinsic dynamical system acting on the attractor, the orbits, you don't need to be super specific. You can come up with a pseudo-orbit. You can sort of think about it or draw it approximately. I mean, no matter what you do, you're always going to draw it approximately, of course, because it's a bizarre set, this fractal. But this approximately drawn pseudo-orbit really represents an actual orbit for the dynamical system, the intrinsic dynamical system that allows you to jump from point to point inside the fractal. Okay? So this is sort of the application to iterated function systems. And then you can sort of go further with this. So one of the things that Barnsley does really is that instead of leaving this epsilon delta, he has like more quantitative estimates. But I decided not to go into that. If you're interested, this is like a very nice topic. It will be good to have a look at. Okay. Any questions about these? Okay, so I want to say something about this perspective. I want to upscale this idea a little bit, which is this idea that whenever you have something algebraic, in this case, the algebraic item is this topological conjugacy. Right? So this is something that you define basically using diagrams. You can say always that, or pretty much always, that instead of having this algebraic property hold on the nose, let me say that the algebraic property holds up to an error. So that is the idea of a quasimorphism. and this is also, this has been very fruitful in many areas of math recently, but I'm just going to give you some idea. So quasimorphism point of view. This is really coming from a different field. So instead of having pseudo, you use quasi, which both of them mean approximately or like in English. And morphism is sort of the highbrow way of saying conjugacy. Okay. So you can say that the conjugacy, a topological conjugacy, is an isomorphism of dynamical systems, if you want to use sort of highbrow language. So what I'm going to do is this. Basically, the whole idea is taking this successor dynamics that I was using to define a pseudo-orbit, I'm going to use an arbitrary dynamical system. So let's say that I have y, g, and then I have x. The only thing that you keep is this uniform error up to delta error. So a quasimorphism from from G to F is a phi delta quasimorphism. If, well, I just need to read what this diagram is saying to me and express it. So I'm going to look at the distance using the metric on x between phi composed with x, composed with g, but I need to start with a y here, comma, f composed with phi applied to y. But I want this to be bounded uniformly in y. That's just a definition. You want to say something like, if I have a delta quasimorphism, I have an actual morphism, which is sort of the same idea, the same shadowing property, but more upscale. And if you're interested in this perspective, I've uploaded a paper by Gromov under the resources. That's, I think, very enlightening. It might be hard to read, okay? Years ago, when I was in grad school, I tried reading it, I remember, and I couldn't read it, but just recently I looked at it again. It made more sense this time, so at least parts of it. So
just get your PhD.
yeah. No, I mean, you're assuming that I'm too bright to understand things, so it takes me a while to understand. Anyway, this is it's a very useful thing. Another way this quasimorphism business shows up is in the context of what is called rotation numbers. So basically, if you have a homeomorphism of the circle, you can associate to it something called a rotation number in such a way that actual rotations, so if I were to look at f of x equals x plus alpha mod 1, that has rotation number alpha, but any other homeomorphism too has a rotation number. That goes back to Poincaré, one of the big names, one of the founders, I would say, of dynamical systems. So this notion of a quasimorphism is very fruitful. Because it's really allowing you to do something algebraic, but up to some error, and then you can sort of negotiate, which we like doing in analysis. Okay. That's all I wanted to say about all this stuff. Okay, any questions? Yes?
Is G acting on
Where? Here?
This exercise at the
Oh.
top of the right-hand page.
Oh, this one?
Right there.
Oh, yeah. Thank you.
Just want to make sure.
Yes. Yeah, of course, this phi is going the other way around than this phi. Always forgetting. Okay. Good. Dimension theory. I'm going to leave this. So today I'd like to give the definition of one version of a topological dimension. Give some exercises about it to convince you that it's not quite nice for our purposes. For many purposes, it is very, very useful, namely for topological purposes, but for analytic purposes, that is to say, when it comes to these like more complicated sets, at least from an analytic point of view, it's not really giving you too much information. So hopefully the rest of today is going to be somewhat lighter. So let's sort of think about different kinds of dimension. So one, of course, notion is the dimension that you learn in linear algebra. You say that the reals, right, is one-dimensional. And then you say Rn has n dimension. Right. This is something that you learn. And of course, what does it mean? You learn in linear algebra, for instance, 2270. That you have to have a set of n vectors that is both linearly independent and spanning. Of course, one of the things that we don't really discuss in a basic course is that this really is dependent on the base field that you're using. Namely, you're looking at R to the n as a vector space over R. If you were to look at R to the n, or maybe say R as a vector space over the field of rationals, what is this dimension? It's infinity. Okay? Even at the linear algebra level, it is very complicated, or it is somewhat confusing, let's say. And similarly, the complex plane relative to the reals is two-dimensional, but relative to itself, it is one-dimensional. And so you see, in the context of linear algebra, then it becomes important what the base field is.
So are you saying that a scalar multiplication?
Exactly.
Okay.
Yeah. So the base field really is restricting the scalars that you can use. So the complex plane is two-dimensional relative to reals because you cannot rotate using a real number, but you can rotate using a complex number. Which is why, for instance, if someone is doing complex geometry or algebraic geometry or whatever, they would call C one-dimensional, which is very confusing for someone like me, but they do it. So, okay. Another thing that is somewhat perhaps part of this is what is called dimensional analysis. This is sort of like of a different flavor, but ultimately this is also a linear algebraic thing. Basically, this is more in the lines of like applied stuff, engineering and physics and stuff, which says that when you're doing something like physics or differential equations even, that is supposed to be somewhat physical. Often numbers are not pure numbers, but they come with units. And when you're doing operations, at the very least, you shouldn't be able to add, for instance, a quantity that is measured in length to a quantity that is measured in time. Right? So there's no such thing as, so I can say, oh, okay, this takes me 1 second, whatever procedure, and then I have whatever, let's say time this, and then 2 units of length. Let's say I have a rod or something like that. And then, okay, you can perhaps multiply them, but this has no meaning. This doesn't have any meaning in this context. You cannot add time to length, apples and oranges and stuff like that. And there is sort of, that's one thing. Another thing is that when you're describing a physical law, for instance, a differential equation, the validity of that law should not be dependent on the specific units that you're using. So when you're saying F equals ma, you're not saying that F equals ma, but you need to measure acceleration relative to in seconds. It doesn't matter, right? So this law is true no matter what you use for m, insofar as it's a mass unit, of course. So you can sort of look into this and you can say that, oh, the units of this equation is m times acceleration, that's length divided by time squared. Okay. So this force, Newton's perhaps, it should be of this form, which then allows you to sort of look further into numbers and stuff. So there's an important theorem in this context, which is called the Buckingham pi theorem. Yeah.
What's the notation you're using for these like square brackets?
Oh yeah, so this is the unit. This is the mass type unit.
Okay.
This is the length type unit, and this is the time type unit. There's, I think, a couple more. I don't use them that often, so I just looked into these yesterday. So, but there's something called Buckingham pi theorem. Which basically is the underlying procedure that allows you to sort of match the dimensions of the left-hand side and the right-hand side. Just leave it at that. It's not that important for our purposes, but probably this dimensional analysis is more important than anything that we're going to cover in this class, in the global scheme of things. Okay. Any questions about these two? Okay, so the rest of today, I'd like to discuss something more high level, but still slightly higher level than these, but still at a lower level, which is this topological dimension. And so that's what we're going to spend the rest of the day. Give some exercises about it. It's very nice. It's a very nice idea. It's not going to be fine enough. It's not giving us fine information. Okay, let's take a 5-minute break, and then when we get back, we'll do topological dimension theory. Okay, welcome back. So the notion of dimension I'd like to discuss is what is called Lebesgue covering dimension. Often you can also see topological dimension, but really within the context of topology, there are so many more dimensions also. Typically for metric spaces that are nice, what we're going to discuss is going to be, it's going to coincide with small or large inductive dimension, but there are these other dimensions as well that I wanted to mention just to sort of pique your interest a little bit. There's this Gromov asymptotic dimension that is sort of like a Corsair invariant. There's this Assouad-Nagata dimension and then Krull dimension and so on. We're not going to use these, but it's good to know that there are all these different types of dimension that are useful in different contexts. Okay, so before sort of formalizing this, maybe I should try to give some intuition, because ultimately all of these, any notion of dimension sort of comes from a certain intuition. There's an intuition as to what dimension should be. So let's say that you look at the interval and you say that is, so the dimension of it should be 1. So that's your intuition. How can you come up with a mathematical object that does associate to the interval the number 1? That's the point. And for Lebesgue covering dimension, this intuition is about this. You take, for instance, the interval. And then this is the closed interval from 0 to 1. And then using small open subsets, or let's be more specific perhaps, using small open intervals, let's try to cover this. Okay? So I want a bunch of open intervals in such a way that when I take the union of them, I get everything. Which means that ultimately, because this is connected, there should be some overlaps, right? So maybe it's going to be like this. Then here's another one. And maybe the next interval that you chose, maybe it was too small, but in a sense, maybe it was redundant. Perhaps it was here. Doesn't matter. And let's take another one like this. And then maybe you took here infinitely many. I'm not saying finitely many. You might need infinitely many that are like this. Okay? But for Lebesgue covering dimension, what you look at is the redundancies. Well, I have a bunch of intersections here and so on, but I don't need all of these. And so if I were to get rid of some of these intervals, what I could do is, if I were smart about how I was covering the whole interval, I could just do this. Then this. You should imagine all of these intervals to be of the same small size. And then maybe here's a final one. Okay. Now, somehow I claim that in this picture, I see the number 1. Namely, that if I were to look at intersections, in other words, how many of the open sets intersect at any given point, sometimes only 1, but sometimes it's 2 of them. So this covering is, in a sense, optimal because the number of intersections is at most 2. So if I were to look at, in other words, what I'm trying to say is this. If I were to look at the number of intervals in my cover that covers this particular point, there's only 1 of them. But if I were to look at this particular point, there are 2. And so I get to cover the interval using arbitrarily small open sets in such a way that no 2 of them intersect, no 3 of them intersect. Okay, so that's giving me the dimension. Dimension should be this minus 1. Okay, so that's the intuition of Lebesgue covering dimension. Any question about this? So now we need some definitions to make this formal. So first, the notion of an open cover. I don't actually need X to be a metric space. A general topological space suffices here, but since we didn't define it, I'm just going to keep it. I'm just going to stick to metric spaces. I'm going to call a collection of subsets of X, which I'm going to denote by curly U, an open cover. Curly U of X is an arbitrary family. I'm not saying finitely many, maybe infinitely many, and so on. X is a family of open subsets of X such that if I were to take the union of all of these open subsets, I have X. So one way to write this is like this. U in curly U, so the union of all elements, all sets inside the curly U, I'm taking it. So this is now a subset in general, but I want it to be equal to X. That's the definition of an open cover. Any questions about this? So in this case, I have two open covers, as you see. I'm going to call, so if I have two open covers, let's say U and V, I'm going to call one of them a refinement of the other one if the following happens. If U and V are open covers of X, let's say that, okay, a refinement from V to U is a function from V, so it's a function that takes sets as inputs and produces sets as outputs, is a function rho for refinement, from curly V to curly U, such that for any V in V, rho of V includes V. For any set in my collection V, if I were to apply rho to it, now I have a set in U, and I want this initial guy to be a subset. Okay. Now what's the idea here? Maybe let's draw some pictures. Okay. So let's start with okay. Let's look at an let's look at a square. So you see, in this notation, I have U, and you should think of it as like this. U is a cover whose pixels are larger, and V is a cover whose pixels are smaller. So in a sense, V is finer than U. So let's say that U covering is something like this. It has these big pixels. Okay. And I'm going to draw the same thing over here. So this is my X. I'm trying to cover the square. And here are the elements in U. So I can imagine V to be like this, perhaps. Yeah, let's keep it like this, okay. So I have two sets in U, let's call them U1 and U2, and I have four sets in V. Let's call them V1, V2, V3, V4. Now you see, what is the refinement here? I'm saying that curly V is a refinement, so there's a refinement from curly V to curly U. Well, what is the refinement? I need to say where each of these should be taken. So V1 this blob is a subblob of this blob, okay? And so is V2. And then V3 and V4 are inside, oh sorry, this is U1. Okay? So maybe I should leave it to you to explicitly write what the rho is in this case. Any questions about this? Okay. Now the point is that I can cover the whole X using the U cover or the V cover. But somehow the V cover, also the elements of the V cover is more controlled. They are more controlled. Okay. And I'm going to say that V is finer, or yeah, let's just leave it at that. V is finer than U. Okay, another thing I need to formalize this intuition of the number of intersections is the multiplicity, or the order of a cover. Let me define it here. So for any x, now I'm going to look at, let's say that I fixed one of these covers. I'm going to look at the number of cells, or in other words, the number of pixels in my cover that cover this particular point. So look at this. So U in curly U such that X is in U. This is a subcollection of curly U. It's a collection of sets. Now I'm going to look at the number of it. And let's call this M sub X of curly U. It depends on the base point X. This is what is called the multiplicity of curly U at the point X. Then again, following the intuition, I should take the max of this over all x's. And let me denote this by M of U. Now this number is going to be it's going to be an integer, or it's going to be infinity. At the very least, it is 0, but because maybe, I guess it's not going to be 0 ever. But let's just leave it like this. It's going to be an integer union infinity. Yeah, it's going to be at least 1 actually. Because I started with an open cover, I know that given any x, there's at least one U in U, such that x is in U. Which means that M sub x of U is at least 1, which means that if I were to take the maximum over all x's, that's going to be a number that is at least 1. Okay. Any questions so far? Okay, so now we can define topological dimension. So let X be a metric space. It's Lebesgue covering dimension, which I'm going to denote by dim sub L of X. Oh, covering. dimension dim sub L of x, this is going to be a number. This is kind of awkward, but it starts at -1, and it's an integer, or it's infinity. Is the least n such that for any open cover U of x, there's a refinement of U. So there's an open cover V refining U such that M of V equals n plus 1. So ultimately, you should think of it like this. If I'm saying that the dimension of the space X is n, then there is some cover of it, heuristically speaking, such that if you were to take any n plus 2 sets in that cover, and if you take the intersection, that intersection is going to be empty. So there is a cover V such that for any V1, V2, Vn plus 2, distinct of course, if I were to look at the intersection, that intersection is empty. Examples. So of course I should first try the interval, right? Based on this definition, the interval should have dimension 1. And indeed this is true. So x equals 0 to 1 as a metric subspace of the reals. Well, so I start with an open cover. What does this mean? It means that for any set U in curly U that is non-empty, and some of them have to be non-empty, of course, because it's a cover after all. Well, for any non-empty element here, I can take a point in that cell. That cell is open, which means that that cell has to contain an open interval. So for any non-empty. Okay. First, an exercise. I can assume that U is finite, in fact, without loss of generality. U is finite. And in fact, there's this statement that some of you know, but still, let me just write it here. A metric space is compact if and only if any open cover has a finite subcover. So you can just discard all but finitely many elements in your cover, and that's still a cover. And that's an equivalent condition for compactness. Finite U prime, which is a subset of U, such that if I were to take the cells only in U prime, that's still a cover. So I can assume that U is finite. Then for any x, or rather, for any U in curly U, pick a point in U, then there's a delta, such that x minus delta, x plus delta inside U, but because I have finitely many, I can just assume this delta to be uniform in x, so that I have ultimately, there are some things you need to say still, but ultimately I have this covering that I gave before. There are some details that I've discarded, didn't mention, but let me just perhaps say exercise here actually. This is sort of the general idea. Okay, so this intuition does work. Maybe it gets a little technical, but this is what it is. Any questions about this? Yes?
Orange block is really confusing me. Just the fact that we have n plus 2, I don't know, maybe I think like n minus 1 would do that, but I guess I don't understand.
Okay, so in this example, I have a cover that is arbitrarily small, and pairwise intersections may not be empty, but 3, okay, so that's why plus 2. Yeah. Okay. Running out of time. Some exercises about this. It's a very nice exercise to show that the Cantor set has topological dimensions 0. And the Sierpinski gasket has topological dimension 1. Ultimately, it's always going to be an integer, which is why it's not fine enough of an information. So Sierpinski. S1. If you have a subset that is closed, then the dimension of the smaller set is bounded by the dimension of the larger one. I thought of some examples where this doesn't work if A is not closed, but I couldn't find. And there are a couple more properties. This is like an important topic for topology, but not that much for us because of essentially this example, this exercise. Okay. Still, it's good to know. This is one of the more popular notions of dimension that people use. Okay, I think that's it for this week. Next week, we're going to switch to box dimension and Hausdorff dimension, which are a lot more interesting, and we're going to have more to say about them. Thank you.